Welcome to a lesson on the basic trig identities. In this video we will introduce the fundamental trig identities and we'll look at how we can use those identities along with some substitution and other algebra to simplify expressions, and then how we can verify or prove that other equations are actually identities. Before we get into all that, let's first just talk about what an identity actually is, and let's compare it to what we think of when we think of an equation. So we know that an equation is an expression that states that two things are equal to each other. Okay? You have something on the left is equal to something on the right. And we know that an equation can be true or false, and whether it's true or false depends on the variable. So if you put 0 in for the equation, it might be true, but if you put in 5 for the variable, the equation may become false. So that's an equation, right? When we solve an equation, we are rewriting it as equivalent equations. Okay, so when you go through the algebraic process of adding 5 to both sides of an equation, you get an equation that is equivalent to the previous equation. It looks a little different, but it is equivalent, meaning it has the same solutions. When we solve an equation, we assume that it's actually true. And because of that assumption, that's a assumption that allows us to do things to both sides of the equation. So having a statement that's true, an equation that's true, allows us to add 5 to both sides of the equation and have something that is still equivalent. So we are able to work on, you actually have to work with both sides of the equation. You have to balance the equation, so to speak. Maybe that's a phrase you might have heard. And then we try to find the values that make the equation true. There are some that make it true, and the rest of the x values or variables will make it false. So usually when we have equations, we're trying to solve. So what is an identity? An identity is an expression that states that two things are equal to each other, so if you notice, that's the same exact sentence statement that I had for equation. So an identity is an equation. It says that something on the left is equal to something on the right. So why do we have this whole big deal? Well, an identity must always be true. It must always be true. It doesn't matter what you put into the variable, it still has to be true. It doesn't matter if you put in 0 for x, or -5 for x, or 5 billion for x. It has to still be true. So we're going to look into how we verify, how do we prove an identity is true. Well, when we're doing that, you can't assume that it's true, which, because it was when we assumed the equations were true, that allowed us to work both sides of the equation. So because we are not assuming it's true, that means we cannot work on both sides of the equation at the same time, which means that we have to work on both sides of the identity separately. So usually the strategy is that we're going to take either the left or the right. You can kind of work whichever side you want, but we're going to try and take one side and rewrite it so it looks the same, so it matches the other side. And it's possible to work both sides, but you're not treating them as an equation. You're working on each side separately, independently from each other. And then we can show that an identity is false with just a single example. So if you have something you think is an identity, and you can find just one number to put in for the x values or for your variable that makes that statement false, so it's no longer true, then that means you have disproven the identity and it is just an equation. All right, so let's actually look at a few examples and just kind of compare a little bit. So let's start with the equation 2x plus 3x is equal to 5. So the question we need to ask ourselves is that always true, or is it only true some of the time? Okay, so when is 2x plus 3x equal to 5? Well, it's only true if x is equal to 1. If you plug any other number in for x, that will not be true. So this is an example of an equation. Okay, what about 2x plus 3x is equal to 5x? Well, 2x plus 3x to 5x, that will be true if I plug in 1 for all the x's, I get 2 plus 3 is equal to 5, which is true. If I plug 0 in for all the x's, I'll get 0 plus 0, which is 0. So that's true. So really, it looks like this is always going to be true. And so we could think of this as an identity. Okay, and it's actually an identity you probably are familiar with, at least from way back in your schooling. If I took the 2x plus the 3x, this is sort of how we can verify that it's an identity. I could take an x and factor it out, which would leave me with 2 plus 3 times an x. Well, 2 plus 3, we could go ahead and compute that. 2 plus 3 is 5. So I have a 5x. So I was able to take the 2x plus 3x and do a little bit of algebra and rewrite it as 5x. Okay, so we used this, we kind of factored it out, using the opposite of the distributive property. We were able to show that it is actually an identity. Okay, I was able to rewrite the left side so that it matched the right side. So it is an identity. All right, let's look at some more. What if we have 3 times the quantity x plus y is equal to 3x plus 3y? Okay, well, that's actually what we just looked at doing. That is that's the distributive property. So if you remember stuff like that from early in your math career, distributive property. This is always true. Therefore, it's an identity. If it wasn't always true, it wouldn't be a property. We wouldn't use it. Okay, it would just be a nice little equation that we'd have. Let's compare that with 3 times the quantity x plus y is equal to 3y. So is this always true, or is it only true for certain values of x and y? Because we have 2 variables. Well, the only time this is true is when x is equal to 0. If I pick any number other than 0 for x, it will be false. So that's an equation. All right, let's look at 2 more. What if we had sine squared plus cosine squared is equal to 1? Well, we actually already know this one. We've talked about it in a previous lesson. This is a Pythagorean identity. So we already know this one's an identity. So here's the question. How important are the squares? In other words, is sine x plus cosine x equal to 1? Well, is it always true, or is it only true some of the time? So let's try a couple examples. What if I did, let's try the point where x is equal to 0. And if I do that, I'm going to have sine of 0 plus cosine of 0. And I want to know, what is that? Is that equal, put a little question mark there, is that equal to 1? Well, sine of 0 is 0, cosine of 0 is a 1. Well, that is actually equal to 1. Now, that doesn't prove that it's an identity, it's an example that worked. Let's try pi. So we have the sine of pi plus the cosine of pi. Is that, so we're going to say equals with the question mark, is that equal to 1? Well, what's the sine of pi? Sine of pi is also 0. What's the cosine of pi? Well, it's -1. Is that still equal to 1? Well, no. -1 is not equal to 1. So this is just an equation. This is right here. This is a counter example. So a counterexample just means that you've shown that it's not always true. It's maybe true some of the time, and which we found an example where it was true some of the time, but we have found an example where it's not true. Okay, so that's our counterexample. So it's not an identity, it's just an equation. So having those squares is important, which it comes out of the Pythagorean theorem So a squared plus b squared equals c squared. All right, so we're already familiar with some identities, like the Pythagorean identities, and there's others that we've talked about as well. So let's just run through those real quick. So our fundamental trig identities include several groups. The first group that we've talked about before was the reciprocal identities. So the reciprocal identities just gave us relationships between sine and cosecant, cosine and secant, tangent and cotangent, and then their reverses, the reciprocals. And then it gave us a relationship between tangent and sine and cosine, and cotangent with cosine and sine. All right, so we know that those are identities already, and they're identities simply just because of the way that we defined the functions. Okay, we know sine is 1 over y. We know we know if sine is y, cosecant's 1 over y. That was just the way it was defined. We knew they were reciprocals of each other. There's some others that we've talked about already. We talked about even and odd identities. So remember, cosine and secant are even, so which means that if you have a negative inside the cosine, you can just get rid of it and think of the cosine as the positive. And then the other functions were all odd. So that means if you have the sine of a negative theta, you can pull that negative out front and compute the sine of the positive theta. And same thing for tangent. Okay, so those are our even and odd identities. And then again, we have the Pythagorean identities, which we just looked at the first one. And then you should be familiar, again, we've talked about this before, but you should also be familiar with the other two as well. The tangent squared plus 1 is equal to secant squared, and that 1 plus cotangent squared is equal to cosecant squared. All right, so let's look at how we can actually simplify or even verify or prove that an identity, that something is an identity. Okay, so let's just kind of look at some basic steps here about how we can go ahead and simplify an expression or prove an identity. And you don't have to use these in any specific order. They are just kind of the options that you have to work with. So one option that you could do is make a substitution. So you could use an identity and substitute it into your expression. Okay, and you've done this before. You know, when you solve equations, sometimes you substitute one equation into another equation, and then that would let you eliminate a variable or something like that. So one thing you can do is make a substitution. Okay, right now we're only worrying about the fundamental identities, but we will, over the next few lessons, we will add more identities into the whole process. So we can make a substitution. Often it is helpful for us to have all the trig functions expressed into an expression that contains either a sine or a cosine. So in other words, try to eliminate tangents and secants, cosecants, and cotangents. It's not always the best option, but more often than not, if you can get it all down into sines and cosines, it just makes life easier. And we'll look at some where most of them, the ones we look at, I think it will be easier, but again, there are some that aren't. You could use some algebra. Sometimes this is pretty easy, sometimes it's not. Some of the easy things would be like factoring. So if you can see a common factor, you can pull it out. Or maybe you have some quantity squared, and so you can expand it, you FOIL it out. Sometimes things are a little harder. Sometimes you need to multiply by a 1, which usually just means you're trying to find a common denominator. Sometimes you might even have to do something weird like adding a 0 in. Okay, so we'll look at a few examples of how we can simplify expressions. Now, if we want to verify an identity, which just means we want to show that we have some equation that we think is an identity, and we want to make sure that it is, so it's true always. The first thing, you can't assume it's true, okay? Which may not make a lot of sense to you, but what that means is that you have to work on each side of the equation symbol independently. So you can't add a 3 to the left side and then add it to the right side as well just to balance things out. You have to pick one side and work with it. Okay. Now again, you can technically work both sides of the equation, but you're working them as separate things, separate expressions, and your goal, your end goal is to try and get those two to match. But you're not doing this, you're not balancing out an equation. You're working with one side to rewrite it in the other. So again, you cannot add, subtract, multiply, divide something to both sides of the equation. You can't take the square root of both sides. You can't multiply. You can't square both sides of the equation. Okay, so you're working on them independently from each other. Okay, so we've talked about all the stuff. Let's just look through some examples. And again, remember, substitution, convert sine and cosine, or do some algebra. Those are really our three main steps. All right, so for this first example, we have the quantity of 1 plus sine of y times the quantity secant y minus tangent y. Now, when we're doing these identities, when we're trying to simplify them, one of the hard parts with this is there's often no right way, no single right way to do it. Okay, I'm going to go through one process. It may not be the best, the easiest, but it's one process. You may find a completely different process. It'll probably have similar steps. Maybe it changes the order in which you do some steps. But again, there's no one single way to do it. There's multiple ways to simplify it. So again, my options are to make a substitution, to convert things to sine and cosine, or to do some algebra. Okay, so I'm going to go ahead, since I have the parentheses in here, let's go ahead and do the algebra first. Okay, so if you have two parentheses, two quantities multiplied together, and there's a subtraction or addition sign in the middle, that means you have to FOIL. So hopefully you all remember how to FOIL. You do the first, the outside, the inside, and then the last. So if we take the first number, that's the 1, and then the secant. So 1 times a secant of y is just a secant of y. So that's the first. We're then going to do the outside. So that's the 1 and the tangent. So we have 1 minus a tangent, so minus tangent y. So far we have secant y minus tangent y. And then we do the insides, which is sine of y and secant y. So we're going to add a sine y and times a secant y. And then we're going to do the last, which is the sine times the tangent. So we're going to have minus a sine y times a tangent y. Okay, so we did a little bit of algebra. So from here to here was just some algebra. We just FOILed. And I mean, I don't know if it's a simpler expression right now, but our goal is to make it simpler. So right now we have 4 terms. They all have trig functions in them. Some of them have sine and cosine, some of them don't. So we've done some algebra. Let's try and do a substitution. So let's use the substitutions that we have so far, which we know secant. This is one of our reciprocal identities. We know secant is 1 over cosine of y. And then minus, so secant becomes 1 over cosine, minus tangent, which I can do a similar thing. Tangent, we know, is sine of y over cosine of y, plus sine of y times, we have another secant, so I could rewrite that as 1 over cosine of y. And then minus sine of y times another tangent, which is another sine y over cosine y. Okay, so we did some substitutions. We used just some reciprocal identities for the most part, substitutions. And we actually converted everything into sine and cosine as well. So if you look, all my trig expressions are written in sine and cosine. So all the substitutions we used, went ahead and converted everything into sines and cosines. All right, so let's just do a little bit of algebra and simplify the stuff we have. So we have 1 over cosine y, which doesn't change, minus sine y over cosine y, which doesn't change, plus we have a sine over 1 times a 1 over cosine. Well, when you multiply fractions, you multiply the top and the bottom. So this becomes sine y over cosine y. Minus, we have another sine over 1 times the sine over cosine. And sine times sine is going to be sine squared y. So we have sine squared y over just a single cosine. All right, so we just did a little bit of algebra. Okay, so is there anything that we can simplify, cancel, combine together so far? Well, we do have a minus sine y over cosine y, and we have a plus sine y over cosine y. So these two actually cancel each other out. So we're left with 1 over cosine y minus sine squared y over cosine y. So again, we did some more algebra. Okay. Well, we have two fractions, 1 over cosine y and sine squared over cosine y. And if you notice, they both actually have the same denominator. So we could combine those together into a single fraction. So we'd have 1 minus sine squared y, and that would all be over a single cosine y. So again, just doing some algebra. Okay, so do I have a relationship, an identity that we're familiar with that deals with sine squared? And so oftentimes when you see sine squared or cosine squared or tangent squared, any of the squared functions, a light bulb should go off in your mind thinking Pythagorean. Okay, so let me come over off to the side here. I know that sine squared y plus cosine squared y must equal 1. So look at what we have in our simplification process so far. I have 1 minus sine squared y. Is there a way I could take my Pythagorean identity and write part of it to match that? Well, yeah, I have this 1. If I were to take the sine squared and subtract it over to the right side. So if we subtract that, we're going to have cosine squared y is equal to 1 minus sine squared y. So notice that this is the same thing that I have in my fraction over here that we're simplifying. I can make another substitution. So I'm going to replace this 1 minus sine squared with just a cosine squared. So this is going to be a cosine squared y over a cosine. So here we just did a step of, not algebra, that was actually a substitution. We're almost done. If you have something squared divided by just itself, not squared, the squareds cancel out. And so when we're done, we're going to have cosine of y over 1, or if you just want to think of that as cosine of y. And so again, we're just doing a little bit of algebra. Okay, so what we've been able to do is take this more complicated expression, 1 plus sine y quantity times the quantity secant y minus tangent y, and simplify all of that down into a simple expression of cosine of y. So cosine of y is equal to the entire expression we started with. Now again, this is the particular process I followed. You could have followed a different process. Okay, it would have had similar steps, just maybe in a different order. So where I FOILed first, maybe you would have rewritten the secant and the tangent as 1 over cosine and sine over cosine. So you would have been doing what I did on my second step. You would have been doing on your first step. But you're still going to have to FOIL it out, right? So it would be different, different order of steps, but generally the same steps, okay? And then there's other ways to do the identities that I did down here, the algebra, the 1 minus sine squared. There's other ways to get around doing that, but it's still going to involve doing using that Pythagorean identity in some way just to get it simplified. But in the end, you should end up with the same expression, cosine y. All right, let's try another example. So we have the quantity 2 minus 2 cosine x times the quantity 2 plus 2 cosine x. Okay, so again, the process I work through here, to some extent you may be able to do something a little different, maybe not at first, I don't think, but eventually you might be able to do a few different steps. But again, there's often not just one way to go about simplifying it. So my first step, again, I see two quantities. I see the 2 minus 2 cosine x, and then I see the 2 plus 2 cosine x, which again, I see that, and I'm again thinking I need to FOIL. So let's go ahead and FOIL this out. So we take 2 times 2, which gives us a 4. We take a 2 times a 2 plus cosine x, which is going to give me a plus 4 cosine x. We then take a minus 2 cosine x times a 2, which is going to give me a minus 4 cosine x. And then we take a negative 2 cosine x times a plus 2 cosine x, and that will be minus 4. So cosine times cosine is cosine squared. So when you multiply something by itself, it's squared. So now that we've FOILed it out, is there anything we can do to simplify it? Maybe some algebra or substitution? Well, looking at this, I have a positive, a plus 4 cosine x, and I have a minus 4 cosine x. So those two are going to subtract out. So that leaves us with a 4 minus a 4 cosine squared x. Okay, so is there anything we can do to further this? There's some algebra we could do. And the other thing I mentioned is if I see a cosine squared or a sine squared, I should be thinking Pythagorean theorem. So there's a couple things I could go with. I'm going to do the algebra first. So I look at this and I see both of these, both the 4 and the 4 cosine squared have a 4 in it, and so I'm going to pull that out. When you factor a 4 out, you're left with a 1 minus a cosine squared x. That should look similar to what we saw in the previous example. So let me go over here on the side. I know that sine squared x plus cosine squared x has to equal 1. This time I want it to look like 1 minus cosine, so I'm going to subtract the cosine over. So that means I have sine squared x is equal to 1 minus cosine squared. So I'm going to replace this 1 minus cosine squared with the sine squared. So we're going to have 4 times a sine squared x. And I don't need the parentheses anymore. I could just write that as 4 sine squared x. Okay, so we were able to take these two quantities, 2 minus 2 cosine x times 2 plus 2 cosine x, and through some algebra and a little bit of substitution, we were able to get it all the way down to just a 4 sine squared x. All right, let's take a look at an example that is a little tougher. So we have 1 over the quantity of secant x plus 1 minus the fraction 1 over the quantity of secant x minus 1. So again, the possibilities here is that we could do a substitution. So really the only substitution we have is secant x. We know secant of x is 1 over cosine. So that's one option. There's really nothing else we have to substitute, so we could, the other option is to do some algebra. And we can go, again, there's different ways to go through this. Let's just try, let's just pick one and run with it. So let's first, let's get a common denominator. Okay, so if I have secant x plus 1 and secant x minus 1, then my least common denominator would be their product. So we could do secant x plus 1 and we could do secant x minus 1. So let's FOIL this out and see what we get. So we would have secant x, or secant squared x So secant times secant is secant squared x. And then we'd have the secant x times a minus 1, so minus a secant x. And then we have a plus 1 times a secant x, so plus a secant x. And then we have 1 times a minus 1, which would be a negative 1. And so that turns out to be secant squared x minus 1. Okay, so we could, if you remember how we do common denominators when we're doing fractions, this is one of those algebraic steps, is we can take things and multiply by 1. So I'm going to take each fraction and multiply it by 1. Now, the nice thing about 1 is it can look like anything. There's infinitely many ways to write fractions that make up a 1, as long as the numerator and the denominator are the same. So what I'm going to do is I'm going to take the first fraction, 1 over secant x plus 1, and I'm going to multiply it by the fraction of secant x minus 1 over secant x minus 1. So I'm multiplying top and bottom by the denominator of the other fraction, minus the other fraction, 1 over secant x minus 1, and multiplying it by 1, which this 1 is going to be the other denominator, so secant x plus 1 over secant x plus 1. So when you multiply these together, the denominators are going to multiply. So that's where the secant x plus 1 and the secant x minus 1 are going to come into play. So for the first multiplication, I'm going to go ahead and rewrite what the denominator is going to be. My denominator is going to be secant squared x minus 1, because that's the secant x plus 1 times the secant x minus 1 becomes secant squared x minus 1. And then the numerator is a 1 times the secant x minus 1. So we are just left with secant x minus 1. Minus. On the second part, again, we have the secant x minus 1 times the secant x plus 1, which we already did the algebra over here. We know that is secant squared x minus 1. And in the numerator, I have a 1 times the secant x plus 1. So it's just going to become a secant x plus 1. All right, so I now have fractions. So that was sort of the idea where you multiply by 1. I can now do some algebra because I have two fractions with a common denominator. So let's combine the fractions together. So with a single denominator now, we're going to have secant squared x minus 1. And in the numerator, we are going to have a secant x minus 1, and then minus the rest of it, the second numerator. So we're going to have minus a secant x and minus a 1. So remember, you have to distribute that subtraction. So it's minus the secant and minus the 1. Okay. Now, what happens? Well, if you look at this, we have a secant x and a minus secant x. So those actually cancel out, which makes a minus 2 over a secant squared x minus 1. So to simplify this a little further, do we have anything that relates to secant squared? Well, again, and we could have done this earlier actually, but we do. We have an identity. We have one of our Pythagorean identities again. So whenever you see something squared, think Pythagorean theorem. We know that tangent squared x plus 1 has to equal secant squared x. So that's that's the second version of the Pythagorean identity. So how do I relate this to this secant squared x minus 1? Well, if I can take this plus 1 and subtract it over, then on the right side I'll have secant squared x minus 1, which is what we're looking for, and what's going to be left on the other side is a tangent squared x. So I can take this tangent squared x and replace it down in the denominator here. So we have equals a negative 2 over a tangent squared x. You could probably leave it like that if you want, but one other thing we could do is, what's the reciprocal of tangent? Well, I know tangent is 1 over cotangent, which means cotangent x has to equal 1 over tangent of x. So I have a 2 over tangent squared. So I could leave the minus 2 where it's at, but I could rewrite the over tangent squared as just a cotangent squared. Okay, you don't necessarily, I guess, maybe have to do this step. You could leave it as the fraction, but usually we like to not have fractions if we don't have to. So I would say our final answer is a negative 2 times the cotangent squared of x. Again, that was a little harder because we had the fractions in there and we haven't used one of the secant squared, tangent squared identities yet, but that's how we could. All right, let's try another example here. So we have our fourth example, which is the cosine of negative theta times the sine squared of theta plus the cosine cubed of theta. So right off the bat, first thing we should see is this negative. Okay, we're just trying to simplify this expression, but this is the only thing that has a negative on it. Okay, the other trig functions all just have a regular theta. So we want to use our even-odd identity. And so our even-odd identity says that the cosine of a negative theta is just equal to the cosine of a positive theta. So we can get rid of that negative. So the first thing I'm going to do is just a little identity, even-odd identity. Rewrite this as the cosine of theta times sine squared of theta plus a cosine cubed of theta. Now, let's see if we can do, there's really no identities we can do, not yet anyway. We do have a sine squared, but I don't have a cosine squared to go with it. We could go ahead and make a substitution here if we want, and that would be slightly different than what I'm going to do here. I'm going to do some algebra first though. I have a cosine on my first term, and I have 3 of the cosines on the second term, so I'm going to factor out 1 cosine. Again, you could do this step differently. You could replace the sine squared with the Pythagorean identity, but I want to do my algebra first. That's just personal preference. You can do it however you want. So if we factor out a cosine of theta, we're left with a sine squared theta plus, if you have cosine cubed and you pull 1 away, you're left with a cosine squared theta. And if you remember, sine squared plus cosine squared is equal to 1. So I have the cosine of theta times a 1, which just turns out to be cosine of theta. Okay, so we took this more complicated expression and we were able to rewrite it as just cosine of theta. All right, just to kind of finish things out, let's look at a few examples of how we can verify or prove identities. So the difference here is that we already have an equality. We're saying that something is equal to something else. The problem is we don't know if it's always true. Okay, now I'll just tell you, for everything that we're going to do, I'm not going to give you something that's not true. If I say verify an identity, I'm not going to give you one that doesn't work. Okay, so it should work, hopefully, unless I make a mistake somewhere. But so we want to show that the tangent squared of alpha minus the sine squared of alpha is equal to the tangent squared of alpha times the sine squared of alpha. So we want to show that whether it's a subtraction or a multiplication, it's the same thing. Okay, so remember, with identities, we're not going to assume it's equal, so we have to work on both sides independently. So, so many people are tempted to do this. We're going to add sine squared alpha to both sides. So many people are tempted to do this right off the bat because it looks like an equation, okay? You can't do that. This is not an equation, so we can't do that. So let's just, again, scratch that whole thing out. We have to work with one side of the equation at a time. So I'm going to go ahead and also draw a line down the center. So I can work with the left side. I can simplify tangent squared alpha minus sine squared alpha. I can do stuff with that. I can also do stuff with tangent squared alpha times sine squared alpha, but I can't cross the line in the middle. Okay, so let's start with the left side here. We know tangent squared minus alpha, or tangent squared of alpha minus sine squared of alpha. Really right now the only thing I can deal with is this tangent squared, and I know tangent squared is sine squared of alpha over cosine squared alpha, and that's minus, so since this is a fraction, let me write this also as a fraction. This will be sine squared alpha over 1. Okay, so that is equal to the line above it. I've just done a little bit of simplifying basically. So I'm trying to combine two fractions. I have a subtraction here. How do we subtract a fraction from each other? We need a common denominator, which is going to be the cosine of alpha. So the first fraction we can just leave alone. So we have sine squared alpha over a cosine squared alpha minus, so the second fraction has a 1 in the denominator. It needs a cosine. So it's like I'm multiplying this thing by 1 again, which that 1 is cosine squared over cosine squared. So we're going to have sine squared alpha over 1 times a cosine squared alpha over cosine squared alpha. And that's going to be sine squared alpha over cosine squared alpha minus sine squared alpha cosine squared alpha all over just a single cosine squared alpha. Don't be tempted to cancel the cosine squareds, because if you do that, you just go back to where you were above. We now have a common denominator. That was the whole point of what we just did. So let's combine our fractions together into a single one. And we get sine squared alpha minus sine squared alpha times a cosine squared alpha. And this is all over a cosine squared alpha. So the numerator, what can we do there? But we have two terms, each one has a sine squared, so let's factor that out. So we factor out a sine squared alpha. When you take the sine squared away from sine squared, you're left with a 1, minus, when you take the sine squared away from the cosine squared, you're left with just the cosine squared. So we end up with a 1 minus cosine squared alpha, and that's all over cosine squared alpha. Okay, you may already see where we're going now. Okay, I have a sine squared alpha. I have a 1 minus cosine squared. So, and we've already dealt with this. What do we do with 1 minus cosine squared? Again, we know sine squared alpha plus cosine squared alpha must equal 1, which means sine squared alpha would be equal to 1 minus cosine squared alpha. So I'm going to replace that 1 minus cosine squared with a sine squared. So that gives me sine squared alpha times another sine squared alpha all over cosine squared alpha. Okay, you kind of have to build up your algebra muscle, so you got to exercise your algebra here. So we have sine squared times sine squared over cosine squared, and just like we did before, I'm going to kind of break it apart as separate fractions. It's a multiplication. I'm going to rewrite this as sine squared alpha over cosine squared alpha times sine squared alpha over 1. Now, why did I do that? Well, what am I trying to get to again? Tangent squared times a sine squared. Well, what's sine squared over 1? Sine squared. What's sine squared over cosine squared? It's tangent squared. Okay, so it turns out that this is actually tangent squared alpha times sine squared alpha. And so we've been able to show that this is, in fact, this left side is actually equal to the right side. And I never did anything on the right side. Okay, now, I was all just simplifying the left side. Now, it's possible maybe we would have worked maybe halfway down the left side and gotten stuck and be like, just kind of scratching your head, not sure what to do. So jump over and start doing some stuff on the right side. And hopefully as you start doing stuff on the left and the right side, you'll start to see things get closer to each other, and then you can kind of finish it up. But again, I never did anything where I added something to both sides of it as an equation, because it's not an equation. it's an identity, and we're trying to show that it's actually true. I'm not trying to solve it, I'm trying to show it's actually true. All right, let's look at a second example. This one's a little bit more complicated. So we have the fraction cosine of x divided by the quantity secant x sine x. And I want to check to see if that is equal to cosecant x minus sine x. Okay, so I'm going to do kind of a similar thing I did before. I'm going to draw kind of this line down the middle here. I don't want to cross that line. Okay, I can work both sides of the line. I just can't do the same thing on both sides. Like I'm not going to add a cosine or add a sine to both sides of the equation. You have to work with each of them separately. So let's start with the right side just for fun here. So I have a cosecant x minus sine x. The only thing really I can do with that is I know cosecant is the same thing as 1 over sine x. So we have 1 over sine x minus another sine x, which if you're doing a fraction and a whole number, you need common denominator. So this is 1 over sine x minus, so think of this sine as over 1. If I want to turn that 1 into a sine, I'm multiplying top and bottom. So sine squared x over sine x. And then I could even combine those together now because I have a common denominator. So I'd have 1 minus sine squared x all over sine x. And this 1 minus sine squared should look familiar because we know sine squared x plus cosine squared x is equal to 1, which means cosine squared x has to be the same thing as 1 minus sine squared x. So I can drop a cosine in there. So that equals cosine squared x all over a sine x. Okay, so just compare where I'm at with where we want to be. So I have a cosine, I actually have a cosine, 2 cosines on the top because it's cosine squared, and I have a sine on the bottom. Okay, so I could even break this apart and rewrite this as cosine x times another cosine x all over sine x. So look at where this is at. Okay, I have a cosine on the top and a sine on the bottom. So that's already 2 of the 3 terms in this. I have a cosine on the top and a sine on the bottom. I just have this secant still here. Somehow or other I got to move something around so I get a secant. So let me pause on the right side and let's jump over to the left side and see what we can do with it. So on the left side, I already have sines and cosines, so let's replace that secant. So we know we have cosine of x over something. So secant x we know is 1 over cosine x, and that's times sine x. Okay, so in order to simplify, there's several options that we could take. You could think of dividing this 1 over cosine as a reciprocal and multiply it. It's a little confusing because you have this times sine down here. We could multiply the whole fraction by a 1, which was cosine over cosine, and that would work. Or we could maybe just simplify this denominator. So there's several ways we can do this, but let me go with that third option here. Let's combine the 1 over cosine times the sine. So we know we have cosine x over, so we have a big fraction, cosine x over a denominator, and the denominator itself is a fraction, sine x over cosine x. Okay, so I think this is maybe the most straightforward, easiest to follow. I have a fraction where I have a number divided by another fraction. So if you remember dividing fractions, which I know how much you all love fractions, but when you divide by a fraction, you multiply its reciprocal. So that means we're going to have a cosine x, and if you will, think of it as cosine over 1, times the reciprocal of sine over cosine, which becomes cosine x over sine x. And if I do that multiplication, that's going to turn out to be cosine squared x all over sine x. Now, let's stop here. where have I seen cosine squared x over sine x? It's right there. So I've been able to say, I've been able to take the left side of this identity, of this expression, and I've been able to simplify it down to a point. And then I've been able to do some different stuff on the right side, but still simplify it down to the same thing. So I've been able to show that yes, the left side can be expressed as an equal expression to the right side. So because these two things match, I know that the identity is true. All right, let's look at one more example and then we'll be done. So again, this one's kind of a complicated one because we got fractions in here again. So we have the fraction 1 over 1 minus sine theta minus the fraction 1 over 1 plus sine of theta, and we want to show that that is in fact equal to 2 secant theta tangent theta. Okay, and again, I'm going to kind of do the same thing. You don't have to do this, but I just like to do this so I keep things separate. I'm going to draw the line down the middle. Let's start with the right side again. It's often helpful to start with the most complicated stuff, but we'll just start with the right side. So I have 2 secant theta times tangent theta, and I'm going to use our reciprocal identities. So I know I have, and those, since those are fractions, I'm going to write the 2 as a fraction as well. So I have 2 over 1 times secant, which secant is 1 over cosine theta, times tangent, and I know tangent is sine theta over cosine theta. So let's just multiply those 3 fractions together. So in the numerator, it's 2 times 1 times a sine, which is just 2 sine theta. And in the bottom, I have a 1 times a cosine times another cosine. That's not squared there, just times a cosine. So the end result is that I get cosine squared theta. Okay, it's 1 times cosine times another cosine gives me cosine squared. All right, so let's pause there. There's other stuff we could do, but let's just pause there and jump to the left side. So on the left side, we have 2 fractions with different denominators. So we need to find a least common denominator. Okay, and again, usually with a least common denominator, you're just going to multiply the 2 that you have. So 1 minus sine of theta times a 1 plus sine of theta. If we FOIL that out, we're going to have 1 times 1. So we're going to multiply the outsides, or sorry, the first numbers. Then we're going to do the outsides, so the 1 and the sine, so plus sine theta. Then we're going to do the insides, which is a minus sine theta. And then we're going to do the last numbers, which is a minus sine squared theta. The 2 middle terms cancel out, so we're left with 1 minus sine squared theta. Okay, so I know that's where we're headed on the left side. Let's work through it. So I need to take each fraction and multiply it by 1. The 1 is going to be different for each fraction. For the first fraction, since the denominator is a 1 minus sine, I want to multiply it by 1 plus sine. So we're going to have 1 plus sine theta over a 1 plus sine theta times our 1 over 1 minus sine theta minus for the second fraction, since it's a 1 plus sine theta, I'm going to do the opposite. So we're going to do the 1 minus sine theta over 1 minus sine theta times the 1 over 1 plus sine theta. Okay, so that's equivalent to the statement above. It's equal to it. If we go ahead and multiply out in the numerator for the first part, we have 1 plus sine theta times a 1, which is just 1 plus sine theta. And in the denominator, I'm taking 1 plus sine theta times a 1 minus sine theta, which I can write out the 2 parentheses here. I guess let's go ahead and do that. So we're going to have 1 plus sine theta times a 1 minus sine theta, but we've already computed that, so we know what it's going to be. Minus the second fraction, we have 1 minus sine theta in the top times a 1, so we're going to have 1 minus sine theta. And then again in the denominator, we're going to have these two factors. So we're going to have 1 minus sine theta times 1 plus sine theta. So we now have a common denominator, which we can go ahead and combine the two fractions into one. And let's put them over a common denominator. And we know we can simplify that denominator because we already FOILed it out. It turns out to be 1 minus a sine squared theta. So the 1 plus sine theta times the 1 minus sine theta turns out to be a 1 minus sine squared theta. We already did that over here on the side. So combining our fractions, we have a 1 plus a sine theta in the numerator minus, remember we have to distribute the minus, so it's minus a 1 and then minus a negative sign. So minus a negative makes this plus sine of theta. Okay, and then we can combine like terms. We have a positive 1 and that cancels with the negative 1. We have a plus sign and another plus sign. So if we combine those together, we're going to get a 2 sine of theta over a 1 minus sine squared theta. And again, some of you may be seeing now what's going to happen. I have this 1 minus, so compare the two sides that we have right now. On the left side in the numerator, I have a 2 sine theta. On the right side, I have a 2 sine theta. So I've already matched up my numerators. On the left side, I have a denominator of 1 minus sine squared. On the right side, I have cosine squared theta. Okay, how are those two related? Well, we've already done this before in previous examples. We know sine squared theta plus cosine squared theta has to equal 1, which means cosine squared theta would equal 1 minus sine squared theta. So let's go ahead and write it out instead of leaving it where we're at. So on the left side, we have 2 sine theta over, and this 1 minus sine squared, I'm going to rewrite as cosine squared. And so now, if I compare the left side, I have 2 sine theta over cosine squared theta. And on the right side, I have 2 sine theta over cosine squared theta. Those two things are equal. And so we have just verified the identity.